Here are the notes for section 4.6, which is the graphs of composite trigonometric functions. So we've got combining trigonometric and algebraic functions. This is graph each of the following functions on the interval 2 pi less than x less than, or negative 2 pi less than equal x less than equal 2 pi. Which of the functions appear periodic? All right, so we're going to go to graph. Oops. Get rid of that guy. So make sure your calculator's in radian. So sine x plus x squared. We're going to draw. And we're going to set our view window. So negative 2 pi is negative 6.28. I wonder if I just put 2 pi in. 2 pi. Nope, sure can't. I can. Nah, it'll do it for me. So make this negative 2 pi. Okay, draw. All right, so there's my interval from negative 2 pi to positive 2 pi. It's still a hash mark for still 1, so 1, 2, 3, 4, 5, 6. So this function is not a periodic function. There's no repeating pattern. So this one looks almost something like a parabola. All right, let's try x squared sine x. So x squared times sine x. Looks like that. So we'll zoom out just a little bit. Actually, we'll change our go to negative 10 to positive 10 so we can see it better. There we go. So there's my graph. So something like that. It comes back up. So this is also not periodic. Does not repeat. All right, let's try sine of x squared. Hey, that one's periodic. Nice little wavy line. And the sine of x squared, slightly different. Not the same thing. So this one does give me nice squiggles, but it's not periodic because, so let's be yes. The squiggles are very narrow out here at the end and very wide in the center. Okay, so example 2, verify algebraically that f of x sine of x is periodic and determine its period graphically. So a periodic function just means it has a repeating pattern. So we know that this is true. These are the period if sine is 2 pi. So, and if we plug, if I do f of x plus 2 pi, this would become, sine of x plus 2 pi squared. Well, the sine of x plus 2 pi is the same thing as sine of x, so I get the same thing. F of x and the repeat are the same functions, so it's periodic. So it says determine the period graphically. Okay, so we got to go back and look at the graph. Sine, it was sine of x squared, draw. So if you look, if we can trace it too, so it starts at 0, goes up, comes back down, and at about pi, it starts to come back up again. So the period for this function is just pi, because that's how long it takes to repeat. Okay, so example 3, prove algebraically that is a periodic, sine cubed of x is a periodic function, and find the period graphically, state the domain and range, and sketch the graph. Okay, so once again, f of x plus 2 pi is the sine of x plus 2 pi cubed, but that's the same thing as the sine of x cubed, so sine cubed. So there, algebraically, the repeat gives me the same function they had again. Excuse me. So let's see, if we graph, so find our period. So the sine of x cubed looks like this. So it looks like our repeat is a full 2 pi because I still have my x value here set at 2 pi. All right, where's a good place you can actually see it? That's better. So the period of this function is actually still 2 pi. Domain, well, Domain's still all reals, runs entirely from left to right. The range is between -1 and +1. If you look at your graph. Sine has a range of -1 to +1, so if you cube those values, you still get -1 to +1. -1 cubed is -1 on the low end, +1 cubed is +1 on the high end. All right, find the domain, range, and period of each of the following functions. The absolute value of the tangent of x. So, any place tangent's not defined, the absolute value is not defined, so the domain is all reals, x not equal to pi over 2 plus n pi, where n is some integer. The range is going to be, since its absolute value has to stay above 0, so from 0 to infinity, or excuse me, y greater than or equal to 0. And the period, since we didn't change anything, the period is the same thing as before. Tangent repeats, let's see here, every pi units. So the period of this function is pi. Okay, absolute value of sine x. Domain is all reals. You can plug anything into sine, so you can take the value of anything. The range between absolute value has to stay positive, but sine never goes more than 1. So the range for this function is between 0 and 1. And then the period, let's look at the graph. Option number, absolute value of the sine of x. So if you notice, once again, this is 2 pi. Whoops, can't see it. There we go. That's a full 2 pi, so it repeats twice in that unit, which means this period is pi units. Okay, example 5. Now the graph of f of x, 0.5x plus sine x, oscillates between two parallel lines. What are the equations of those two parallel lines? So what that means is if you look at the graph, 0.5x plus sine x gives me that. So there's two lines, diagonal lines, that the peak never goes more than or goes less than. So let's see here. Okay, so the trick here is that sine has to stay between -1 and +1. So the two lines are 0.5x minus 1 on the low end, and y equals 0.5x plus 1 on the lower end. It'll never go outside those lines. If I had a fancy color calculator, you could see it better. But here's the two lines if I drop them in on top of. So there's the trig function, and then there's the lower one, and there's the upper one. So who knows it stays between, because sine can't go less than -1 or more than +1. So the function, those are the minimum and maximum values at any point in time. Okay, sums and differences. So if you have two functions, y1 and y2, given various things, so if you notice they potentially have different amplitudes, a1 and a2. They do, however, have the same value for b, h1 and h2. Then when you sum them, you can just flat out is a sinusoid with the same period. So if you add any sine function with any cosine function, you still get a periodic function back out. So it says there, for the sum to be a sinusoid, the two sinusoids being added together must have the same period, and the sum must have the same period as both of them. To determine whether each of the following functions is a sinusoid. So if cosine plus sine, they have to have the same period. They both do, because they both have a b value of 1. So this one would be yes. Here, this has a b value of 5. This one has a b value of 3, which means they will not have the same period, so no. This one has a b value of 3. This one has a b value of 2. Different b values, different periods, so no. Let's see here. So this one has a b value of 3/7. This one has a b value of 3/7. This one has a b value of 3/7. So they all have the same period, so yes. The resultant, regardless of what the values of a, b, and c are, it'll be a sinusoidal function, or sinusoidal. So for example, if we graph that top one, I'll show you what we're talking about. 5 cosine x plus 3 sine x. So it's a nice sinusoidal curve. Potentially could be some variation on the sine curve. If I graph the second one, the one that was no, the cosine of 5x plus the sine of 3x. So you notice the heights are all varying. There's not a nice clean single wave. So a sinusoid has a nice wave. All right, so example 7. That f of x is 2 sine x plus 5 cos x. So find the period of f. So in each case, these both have b values of 1. So the period is given by 2 pi over the absolute value of b. So the period is 2 pi. Estimate the amplitude and the phase shift graphically. Okay. Let's see here. So let's look at the graph, I guess. So 2 sine x plus 5 cos x. So there we go. Draw. Looks like that. Okay. So we'll base this off the sine function. So that means this point here should be at 0. So if I can trace it, whoops, I should be able to figure out about what the phase shift is. Negative 1.2-ish would be my guess. Negative 1.19. And the amplitude is, here we go, negative 1.19. The amplitude is going to be the peak here. So it looks like that's about 5.38 be the amplitude. If positive 5.3 on the y value, if you come down here, you'll get negative 5.38. So there you go. All right, give a sinusoid that approximate, okay, well, there's my amplitude. So 5.38 sine, well, my b value is 1, so it's going to be x. I need to move it, so minus, nope, plus, because it needs to be the opposite. It's x minus h. And let's see if I graph this one, 5.38 sine x plus 1.19. Draw, they should hopefully come out pretty much right on, top of each other, so you can't tell the difference. They did draw two curves, so let's see if I can actually, they can draw it again. Menu, graph, draw. There you go. So there's the first one, and there's the approximation. Can't really tell the difference. Okay, so that this function is periodic but not sinusoidal. Well, the not sinusoidal part's easy. This has a b value of 2. This has a b value of 3. So they don't match. So not sinusoidal. To show that's periodic, we just need to show that the function repeats. So essentially that's doing the f of x plus 2 pi. So this becomes the sine of 2 times x plus 2 pi plus the cosine of 3 times x plus 2 pi. But those things, so this would be the sine of 2x plus 4 pi, so distribute the 2, plus the cosine of 3x plus 6 pi. So these values here, 4 pi is a multiple of 2 pi, so it doesn't actually do anything. So this is the sine of 2x. 6 pi also a full multiple of 2 pi, so it's just extra rotations. So this is just the cosine of 3x. So I get the same thing back out. So it is periodic, it will repeat, but it's not sinusoidal. And if I graph it, let's see here, delete them both. The sine of 2x plus the cosine of 3x. So it does have a repeating pattern. You can see the repeat. So low, tall, so on and so forth. So it repeats periodic, but the wave heights are not all the same, so not sinusoidal. Okay, then we have what's referred to as damped oscillation. Excuse me. So the graph of f of x cosine bx or f of x sine bx oscillates between the graphs of f of x and negative f of x. When this reduces the amplitude of wave, it's called damping. this is called the f of x is itself the damping factor. So for each of the following functions, determine if the graph shows damped oscillation. If it does, identify the damping factor as well as tell where the damping occurs. So this is yes. So this is a function of x. So yes, if it does, that is then the damping factor, and tell where the damping occurs. So that means if you're going towards positive infinity or whether you're going towards negative infinity. So this thing damps as x goes to infinity. And if you look at the graph, that makes the where does it damp more obvious. So 2 to the negative x sine of 4x. So there's my wave. Notice, very, very tall, smaller, smaller, smaller. So the waves get smaller as I go to infinity. So for this one is no, because this font thing does not have a value of x in it. So this is not damped. The last one, it would be yes, because that has to have a yes. So the negative 2x is the damping factor. So let's look at the graph to see whether we damp towards 0 or damp towards infinity. It's going to be one of those two typically. So negative 2x cosine 2x, draw. So this one damps towards 0. Because as I come in towards 0 from either side, the wave heights are getting smaller and smaller. It doesn't matter which side. Technically, you could damp towards negative infinity as well, but that's rare. Okay, Mr. Sanchez's physics class collected data for an air table glider that oscillates between two springs. The class determined the data for the equation, blah, blah, blah. Modeled the displacement y of the spring from its initial position as a function of time t. Identify the damping factor. Well, that stuff is the damping factor. To tell where the damping occurs, we'll look at the graph. So 0.22 e to the negative 0.065, use x instead of t, cosine 2.4x, which calculator doesn't care. Let's fix the zoom here. It's hard to see where this one damps. Let's change our axes here. View window. X min will make it negative 0.5, 0.5, scale 0.25, and we'll go start at negative 0.5 or go out really, oops, I did that entirely backwards. Now we want the X min to be that, we want the X max to be 0, we'll count by ones, nope, 25. Y min, negative half, Y max, positive half, steps of 1/4. Let's try this. Hey, there we go. That graph's better. So this thing damps as you go towards the right. So it damps towards, whoops, not X, but T, which makes sense. As time goes on, the thing will bounce less and less and less. Approximately how long does it take for the spring to be damped so that it stays between -1 and +1, or -0.1, +0.1. So what I can do is, what I'm going to do is I'm going to drop another line in at -0.1, and then use my calculator and look at the graph. So stays between, so there the y value, it's right about there actually. It's about 11.5 seconds, 11.6 seconds. So you could actually drop in, whoops, the other one, the positive 0.1. So has to stay above that line and below that one. So trace along the curve until you can find out where it goes. So about, no, there, 11.8 seconds. So you're looking at the graph there. So stay between the two horizontal lines. You're just kind of approximating it. Alrighty, and that looks like the end of the section.